Okay, good morning, good afternoon, whenever you're tuning in. Today's topic is something called implicit differentiation. Sounds crazy. Differentiation really just is the process of taking the derivative. So we're taking the derivative implicitly. Once again, sounds crazy, won't be too bad. Let's take an example of a couple different ways to find the derivative or to differentiate different functions. First one being 3x plus 4y equals 12. We want to find dy dx. We want to take the derivative, right? And this really means the derivative of y with respect to x. Now what we have here is we have an equation in standard form. We know this is linear, but we know it's written in standard form. So one thing that we could do to these linear types of functions is to solve for y. And that is our first method for finding dy dx. Is first we're going to solve for y, and then we're going to take the derivative like we normally would. So how would I do this? So let's see, we have 3x plus 4y equals 12. And if we wanted to solve for y, we would first subtract this 3x term to get rid of that whole thing and to move it over to the other side. We're isolating y. We're getting it by itself. So now I would divide by 4, right? Inverse operations. Now I would divide by 4 over here. Now, what we would have is, let's see, 12 divided by 4 is 3, and 3 divided by 4, that's 3/4. So I could write that as negative 3/4 x. Okay. And really I should, let me go back here. I don't like using that kind of slanted fraction. Let me use to show that that x is right off to the side. Okay. Now, this would be just me solving for y equals, but we really want to get dy dx. So that means that what we need to do is we need to take the derivative. So the derivative with respect to x, derivative of y with respect to x. Let's see, 3 turns into 0. And this negative 3/4, even though it's a fraction, has an x with an exponent of 1. That's really the slope, remember, of that equation. And the derivative allows us to find the slope. So that would just be negative 3/4. The x just disappears. So there's dy dx. Once again, I solved to get y equals, and then I took the derivative. Solve for y, took derivative. 2 steps there. We're going to do a different approach here. And this is what we're talking about today, is there's going to be a different way to get this derivative function, to get dy dx, using something that we call implicit differentiation. So this is actually going to be method 2. It's just a little intro to implicit differentiation, where we're going to actually take the derivative first. So let's actually see what we would do when we take the derivative of 3x plus 4y equals 12. Well, we know how to find the derivative of 3x already. That is just 3. We did that in the last problem. What's different is now we have to take the derivative of 4y. Now, this is only slightly different. We want to treat that y like an x. So if this was 4x, we know that that would just lose the x and turn into a 4. Well, the same thing happens if it's a y, except after we take the derivative, we put a dy dx onto kind of like the back end or tagged along to whatever that derivative is. And then of course the derivative of 12 is 0. So let's just kind of highlight this one little step, and this is going to be the key step with implicit differentiation, is when we take the derivative of a y term, right, that 4y turns into 4. But then, of course, what we do additionally is we just add the dy dx onto it. So when taking the derivative or differentiating or deriving, when taking derivative of y term, we're going to do that like normal, and then we're just going to add a dy dx to it. So 4y turned into 4, as if that were a 4x turning into 4, and then the derivative of y with respect to x. Now, we have taken that derivative, but now our next step would be then to solve for dy dx. So we want to get the dy dx by itself this time. Well, we're still going to subtract that 3. And get a negative 3. And then we would see, let's see, that's 4, like basically times dy dx. So we're going to divide by 4 to cancel that out. And we would get dy dx equals negative 3/4. Well, that's good, because these two things should agree. if math is math, then we should have different alternative methods for solving as long as we arrive at that objectively same answer. So here we have it. Method one, kind of an old school algebraic approach where if you get stuck, you can solve for y and then take the derivative. We would know how to do that based on our prior knowledge. Method two is new information, where if you don't want to solve for y, you could actually take the derivative first and then solve for dy dx to get the same thing. This is where we're going to be hanging out today. We're going to be hanging out with implicit differentiation because it's not only an extra skill that we should have in our tool belt, but there are going to be times when this is their only way to actually find the derivative. Let's take a look at another problem. Here's our next one. Now, in this one, we could once again, as I stated before, solve this for y to get y by itself and then take the derivative. But what we're going to work on today is this implicit differentiation strategy. So step one is we're going to take the derivative. Let's do that. X squared turns into 2x. 4y, once again, let's actually make this a 4y squared. Sorry, I forgot that that was an example that I added on in class. Let's pretend that that was a 4y squared just because I want to make sure that we practice our power rule in here. I could do this with any number of functions, so I'm sorry. And then if I take the derivative now, that would be an 8y, right? Think about that. If that was 4x squared, you know, turns into, let's see, 8x to the first. Well, for a y, that's the same thing. So I still take that derivative, but I just make sure to add dy dx on there. Negative 1x turns into negative 1. Negative 1, since it's a constant, turns into 0. And then 5 turns into 0. Well, I can erase this 0 right here. I don't want to erase the 0 on the other side because I need it to be an equation still. Great. I have taken the derivative and I have been very careful. I'm going to highlight one more time. This is the highlight of the day. And when taking the derivative of a y term, we take it like normal. We just add a dy dx onto it. Now our second step is to isolate or solve for dy dx. Okay, we want to get that dy dx term by itself. Now I can see the 2x and the minus 1 are just kind of hanging out there. So I'm going to subtract that 2x and I'm going to add the 1 to both sides. Right? That's going to cancel them out on the left. And then on the right, I'll be left with just 8y dy dx. So I'm just going to leave that dy dx on the left side. I could have, you know, perhaps moved the 8y dx to the right side and left our regular terms over on the left. It doesn't matter as long as you're very careful with your positive and negative signs. Now, when we isolate dy dx, we obviously subtract those terms first, but then we would divide by 8y. That's going to get that dy dx by itself. Think of that as being multiplied there. And we're going to get dy dx equals, let's see, the 8y's now cancel. Think of that as being like a 1 dy dx. And now we can actually just write this as it is. Here's our answer. So the keys here are making sure that your y's have a dy dx attached to them so that then we could then solve for that dy dx. Getting rid of those regular terms by adding, subtracting, and then dividing by whatever is attached to the dy dx. Now this is one of our answers, but you may see your answer represented, the same answer represented, in a different way. And that's because I actually could have solved this slightly different, right? Remember, I alluded to the fact that we moved the negative 2x and the 1 to the right side. Well, if I had moved this over to the right side as well, the 8y dy dx over to the right side, that would make it a negative. These would have stayed the same signs. And then I could actually end up getting a slightly different answer that would actually end up being the same exact thing. And that answer would be a 2x minus 1 over a negative 8y. And you'll notice here that both of these are the same because if I take this first one and multiply it by negative 1 over negative 1, which is 1 whole, I'll get the second one. All right, so just know this. If you want a really, really quick way to get an alternate answer, maybe you need it on a multiple choice test, think about you know, multiplying or switching all of the signs. Negative 2x turns into a positive, plus 1 turns into -1, 8y turns into negative 8y. And that's true with equations, right? Not expressions, but equations, we can do that. All right, so that's implicit differentiation. If you're stuck on this red one and you're like, what? Okay, focus on that process to get dy dx. We're gonna do one more. This next one I won't change on you and add some exponents halfway through. We're just gonna practice our process here and see what happens when we get something that's slightly different. We're still finding dy dx. Now we could try to get y by itself, but we can see there's actually a y squared and a 3y there. So even if I moved all of my x's to the right side, it's going to be really tough to get y by itself. I'm not even sure I'd be able to do it. So this is where we're really forced to use implicit differentiation. So we're going to take those derivatives just like we normally would. Okay, the 2 comes down, that gives me a 6x. The 2 comes down, that gives me a 2y, both to the first power. But remember, the dy dx is always attached to the y terms. The 4x just becomes 4. The 3y just becomes 3, but because it was a y, we have to put dy dx on it. And then the 1 becomes 0, and the 20 also becomes 0. So this was our first derivative, right? We basically just took the derivative of all those, and I want to once again highlight that since this was a y squared term, we just attached it. Or just a y term, we just attached a dy dx after taking the derivative like normal. Now, it's isolating dy dx. So that means I'm going to move my 6x. Let's keep the dy dx. Let's move the plus 4. The 0 doesn't need to move, so my new equation is going to be 2y dy dx plus 3 dy dx. And then, of course, since we subtracted 6x and a minus, and subtracted 4 from the left, we have to do that to the right. So we get negative 6x minus 4 over on this right side. Now that's isolating the dy dx, but we can see that in this scenario, we have two different dy dx's. Now, I have to give credit to Joseph Cruz. He realized that this is kind of like adding like terms. Those both have a dy dx onto them. I can combine those together. So something like 2y plus 3, even though I can't add them, let's put those in parentheses together as if we were adding them. That is 2y plus 3 dy dx. I like to think about that as factoring. So factor out a GCF of dy dx in both of those terms, right? Factor that out, put the other two together. Now we're almost done, because now we could actually divide in order to solve. So we factor out our dy dx, divide to get dy dx equals, right, to isolate it. What am I going to divide by? I'm going to divide by that 2y plus 3. So I get dy dx equals the negative 6x minus 4 is staying on top. And that's all getting divided by that 2y plus 3. All right, I have parentheses in there, but I suppose I don't necessarily need them anymore. And this would be one of my final answers. I say one of them because it could be represented in different ways. So once again, if you wanted to see this last step written out, I actually divided this whole thing by 2y plus 3. Okay, and that's how I got what I did. Okay, so I said that there was one of your answers. Well, remember how we talked about in that last problem, in order to get a quick alternate answer, which would be like if, for instance, I moved my dy dx's to the right side instead of my regular terms, and then I did that whole process kind of like backwards. All that would mean is that all of my signs would be backwards, and I would have a 6x plus 4 on top, and a negative 2y minus 3 on the bottom. So both of these answers are in fact correct. We should know that, okay, if I do all of this work and get this answer, but it's not a multiple choice item, we should look for the alternate answer where all the signs are changed. And if that still isn't on there, I should look to factor. And if that can't happen, then maybe I would want to go back and try reworking some of these problems. Okay, that was implicit differentiation. So once again, the nuts of it were basically, you have y terms, turn them into dy dx after you take the derivatives. All right, and then you're solving for those using a variety of ways. And in this method, we need to factor both of those out, right? And in order to divide, in order to get that dy dx by itself. That's implicit differentiation. Submit these notes for a classwork grade, and I'll see you tomorrow in class.